Problem 7. A heat pump moves heat from a cooler to a warmer place and is the heart of a refrigerator or an air conditioner. It is used to heat houses. The minimum work input needed to move energy uphill from T cold to T hot is minimum work equals energy moved times T hot minus T cold divided by T cold. Calculate the minimum work needed to move 1 joule of energy from inside a room at T cold equals 295 kelvins to the outdoors at T hot equals 308 kelvins. So let's see, we have from inside a room of 295 kelvins. So we're actually in the summer here. 295 kelvins would be 22 degrees Celsius or 70 Fahrenheit to the outdoor of 308 kelvins, which is 35 Celsius or nice balmy 105 Fahrenheit. So here in part A, let's see. So this would be our part A, where then we're going to come out that the amount of work needed in order to do so is the energy that is being moved, and they just say, you know, take a token 1 joule. So 1 joule times the temperature difference, so 308 kelvins minus 295 kelvins, and divide that by the cold temperature, 295 kelvins. Notice that's a little bit different than the last ones where we divided by the hot temperature. Depends on the engine type. Engine types where you convert heat to mechanical work. In their formula you have to divide by the hot temperature. For here, for a cooling process, so for an air conditioner or a heat pump working in reverse, we have to divide by the cool temperature. On the practice test and on the proctored exam, pay attention that here we use the heat pump in order to heat, and we're back to the hot temperature actually. So pay a little bit of attention here when you take the practice test or the proctored exam. So I'm going to have 308 minus 295 divided by 295, so it's 13 divided by 295, and that comes out to 0.044 when you do that on the calculator, and that comes out to joules because the kelvins cancel. Okay, and then it says from inside a lab freezer at 173 kelvins, so part B, 173 kelvins, to a room at 293 kelvins, so the room is kind of room temperature, 20 Celsius or 68 Fahrenheit, while the lab freezer is minus 100 Celsius or in the neighborhood of minus, is it 150 or minus 200 Fahrenheit, somewhere around there. So pretty cold, and the amount of work comes out to 1 joule times the temperature difference, which I may write as 120 kelvins, I think you can see that, divided by the lower temperature of 173 kelvins, and that comes out to 0.69 joules. All these answers seem like we're getting a freebie because the amount of work that we have to put in order to move 1 joule here is quite a bit less. That's why these are actually not given as efficiencies, but they're called the coefficient of performance, and what it means here is we put only 0.044 joules in order to move 1 joule, and the coefficient of performance is about 20, so we can move 20 times as much energy with a certain amount of work. That's why it's not given as an efficiency, because it would look a ridiculously large number. It's just about moving an amount of heat. It's actually not converting energy. The work, by the way, that is being put in here is then also deposited as heat to the outside. That's why with a refrigerator you're actually a little bit heating the kitchen. Okay, part C says from a helium refrigerator whose inside temperature, so maybe it's this one up here, hopefully not, part C, 4 kelvins, that's minus 269 Celsius, or roughly minus 450 Fahrenheit, to a room temperature of 300 kelvins, that's actually 27 degrees Celsius, or in the neighborhood of, I believe, 85 Fahrenheit, top of my head. And here the work comes out to 1 joule times temperature difference of 296 kelvins divided by the lower temperature of 4 kelvins, and that comes out to 74 joules. So in this case, it's actually that a lot of work needs to be done in order just to move 1 joule of heat out of the helium that wants to heat up in order to keep it cool.